I'm writing a Minecraft server entirely from scratch in Rust, and today I'm going to show you all the code that makes it work. It's now a little over 100,000 lines actually, so it's kind of an interesting milestone, I guess. And let's get right into it. So here we are in Z, that's my editor of choice at the moment. Now there are a couple of modules to this thing. As you can see, there are a couple of top level directories here in the project directory. Each of these, of course, has a very important purpose. So, for example, we have the server module, which is, well, the actual server. But I also have a proxy that is used mostly for testing and playing around with things so that I can just kind of have a program sitting between the server and the client to log things and look at packets and stuff. Then there's also a library that just contains a ton of the shared code between proxy and server and just generally a lot of functionality. Then we have the data, which is just a ton of static generated code. And then there are the data generator tools, which is the actual program that generates the data. And that's also where I want to start. Because for a Minecraft server, you of course need a lot of knowledge about what blocks are and what different items there are and all that good stuff. And I don't want to code all of that from hand, especially because this changes with updates. And I also just want to stay up to date and don't want to spend all my time just doing that. So to automate it a little bit, the official Minecraft server actually allows you to run it in a special way, which I put into this shell script right here. So you run a specific class and just tell it to dump all of its data. And then you get a nice little directory here called just generated. And in there you have some reports. So for example, for blocks, you have a list, a huge JSON file essentially of all the blocks like acacia buttons and what type does it have, what's the block set type, what properties does it have, and what are then the actual block set IDs. So for example, an acacia button that's faced on the floor and facing north and its powered is 10,569. And I don't want to code all of that by hand. As you can also see, this is a very large file, 300,000 lines. Yeah, and that's essentially why I cooked up this data generator tools crate. Now, of course, I could also just use these JSON files and load them in at runtime, but then you not only need the server to run the server, but you also need those JSON files and also the ones with the correct version, because if it's from a wrong Minecraft version, things, of course, then also kind of break. And so I decided to just compile this all into the final binary, and then you have just a little server binary, and then that contains all of the data that you need to run it. Yeah, so that's just the main function or the main file here. It doesn't really contain a whole lot of stuff anymore. I did refactor that recently a little bit, because at first I just made this just dump out all its contents or all the code to the console, and I copy and pasted it manually, and now I'm actually writing that to the correct files automatically, which does make things a little bit easier. We do have little utility function in here still, convert to upper camel case. That's just because Rust wants all of your enum names and structs and all of that to be named in upper camel case, which is not how Minecraft names these things in those JSON files. So I wrote this little function here that just converts that, and also gets rid of that Minecraft colon at the front, so that I can turn, for example, the types that you saw there, which is Minecraft colon button, for example, and just turn that into an enum essentially. Yeah, okay, so let's just look through all of that. So we have 4 modules in here: block entities, blocks, entities, and items. And these are all mostly copy pasted. So for example, for the block entities here, we read in that file, which would be then a file in here somewhere. Generated reports registries.json, right. So for a lot of the things, you just have nice little names like these: Minecraft budding amethyst or Minecraft bush, and then in the protocol in a network, you actually just use numeric IDs, which is a little bit more compact, of course. And this huge registries.json file then contains all of those mappings, or a lot of them at least. And And yeah, for example, also for the block entities. So in here, I'm writing to an output, just as you can see, a little bit of Rust code. Yeah, there are probably smarter ways to do this. I mean, there are like proc macros and that sort of stuff, but yeah, this was just the easiest way to do it for me. So in here, we just load in this giant registry JSON file, and then we just grab the JSON from the block entity type and the entries from that, build out a nice little function here, and then just have an output hash map that's string and U8, and then just have a ton of output.insert statements here. We will of course see those in a second here as well. And then just return that output, and yeah, so that way you can just write huge amounts of code and have all those JSON files in nice, functions that you can then of course call. Yeah, you don't need to worry about like parsing JSON files when you like start up the server and stuff like that. Yeah, not sure if that's like the perfect best way to do this, but yeah, it's been working relatively well so far. So for blocks, I have a little bit more stuff actually, because, well, you're dealing with blocks a lot in Minecraft, of course. Yeah, so there's like one big main function in here, and that just contains like some imports at the top of it, and then we are just creating some functions here again. With blocks, it's a little bit special because there is a lot of blocks in Minecraft. You saw that huge JSON file, of course. And yeah, compiling all of that actually did take quite a little bit of time. The problem is that Rust just compiles uses just one CPU core to compile one single crate. So I split up the blocks into then multiple crates, so it can be compiled a little bit in parallel. So you see like there are 8 crates here in total then for the add functions, which is that thing down here, I think. Yeah, anyways, I'm not gonna like look too deeply at all of that code because it is extremely ugly and it's very hard to explain, and it's just better to, I think, look at the output of that. Yeah. So yeah, down here is actually some code that I've added like manually for like if a certain block type has like right-click behavior. We will see why that's important later. If they're solid, which is currently only used for like entity collisions. So for example, entity doesn't like collide with liquids or with air or something like that. Yeah. Entities is a little bit shorter again. I think that's again just getting a name from an entity ID and getting the ID from a name. So yeah, this is just using that big registries JSON file, nothing special there. And a similar thing, not quite similar for the items. Items are actually in their own JSON file. But yeah, I'm just setting all of that data up here. And now let's just actually look at the data crate itself, because I think that would make a ton more sense. So the data crate itself has like this main component to it, which just, it just imports all the sub crates essentially. Yeah, as I said, this used to be just one giant crate, but it took ages to compile. So now I've just split it up. So now we have, for example, an items crate here, where we set up a struct for the item, and an item has a max stack size, a rarity, a repair cost, and an ID. And then I have just this little function here, get items, and it just returns a giant hash map that just tells you, okay, the Acacia boat or the ID Acacia boat has a max items stack size of 1. It's common, it has a repair cost of 0, and the ID 871. And yeah, this is just a gigantic vector that is built here of these pairs. And then down here we just do a bit of a map, and then we can get a hash map out of that. And if you then want to get an item name by the ID, so doing it in reverse, I'm using just an iterator and using find on that. Yeah, I'm not doing that a whole lot, I think, in my code. So, but that would be something to speed up in the future. Probably just do a similar thing to that. Instead of first building this gigantic vector and then sorting through that, I could just, maybe do a big match statement or something. Yeah, there are probably more efficient ways to do this, but for now, this hasn't been a performance problem, so that's cool. Inventory is something that I haven't auto-generated so far. It's just all the different types of inventories that exist. Nothing too exciting about that one. Entities, get ID from name. So that's just one single, actually two functions. I also have get name from ID, so that's the thing in reverse. Yeah, and that's just one of the things, like, sure, you could go into the wiki and read through all of that and type all of this out by hand. Or you can just not and auto-generate all of that. Let's just look at block entities first, and let's look at blocks last. So for block entities, this is again what we saw in the data generator tools crate, just this get block entity types function that just has a gigantic hash map that contains their ID in text form and in number form. So here I'm setting up the hash map directly and just calling output insert. While for the items, I've made a big vector and then I'm converting that vector into a hash map. Yeah, I don't know. That's just different times, and it's not really a reason to do this in different ways. I don't know. Maybe one is a little bit faster than the other, but it just doesn't really matter, I think. Same with get biome IDs. This I actually did write by hand because there is no way to get the numeric biome IDs and that stuff from the generated data. At least I didn't find it, so I just did that manually. But there's also not that many biomes, just 65, at least that I'm aware of. Maybe there are more biomes in Minecraft now, and I just forgot to add more. Who knows? And then there are the blocks, which is just the majority of the code here. The main crate of that just kind of has some utility functions in it and sets certain things up. So you have functions like get block from block state ID, where you just get the numeric block state ID, and then you get returned the entire block, which contains things like the block's type and its states and the properties. So for these functions, I always pass in the block states. We will look at them separately now in a short while here. And I do that just so that I only have to generate the block states hash map once, because that actually does take a little bit of time. I mean, it's on the order of like milliseconds, but for certain things that certainly matters. I mean, one tick in Minecraft is 50 milliseconds. So if you just spend a few milliseconds of that just building this gigantic hash map every time, then you're just wasting a ton of time. So I'm now generating this only once at startup, and then I can just pass it around wherever I need it. Get block state from block state ID is also then just getting a state, which is then the ID, it's the default state, and then the properties of that state, which we will, of course, also take a look at in a short minute here. Get block name from block state ID, just converting the numeric ID to string again. Getting a block from the name, so again, just why am I getting AR? Oh, that's just if I can't find the block. Okay. I think I did that just like 2 weeks ago because that was when I was optimizing things. But I think this right here may have been in response to a crash because Minecraft kind of changed things a little bit So I just added a default state here. So if you pass in the block's name that doesn't exist, you just get error back out, which is maybe not ideal. Maybe there should be an option or something. Get raw properties from block state ID. So that is used, I think, for when saving the world, just turning everything into NBT. So when the property fence gate power is true, then that's powered and true, and again, a function I don't want to code up by hand. and then getting the blocks ID from raw, that's then when loading the world. So because all the block states are then just strings, and I don't want to deal with strings there in my code, I just want to have nice little enums. Yeah, this is actually a function we did optimize in that video that I did just a few weeks ago, where we tried to optimize world loading. So you may already be familiar with this function. Yeah, so we just try to get the entire block, and then we take the properties, which is a vector or an array actually, and then we just look at what kind of type we're dealing with, and then we're looking at that array and just filtering everything down until we get that like one block state ID back out. Let's actually collapse this. Yeah, this is actually everything. And so this is also a 5,000 line function. So again, something I do not want to maintain by hand. And then there is get type from blocks ID is also its own crate, just because that's also extremely long. This was also for just performance optimization, I think. So again, I could just take the entire gigantic block states hash map and find and filter that down, but with like I think it's some 30,000 different block state IDs, that's also not very efficient. So now I have just a gigantic match that helps me to just get the blocks type from a block state ID, which I apparently needed somewhere. And yeah, I know the code could be a little bit more compact if I had like ranges here everywhere, but this was just the easiest to generate, and it works, and it's faster than whatever I had before, so that's nice. And then there's this gigantic get blocks function. This is, again, as I said, only called once at startup, and then builds this gigantic hash map of the strings and the blocks, so the like blocks ID in the string form, and then the block, which again, block type, then the different states and the properties that the block has or can have. And yeah, this is just, we're building a big hash map, and then we're calling all these add functions here. These then take a mutable reference to the output, and we're returning the output. And then all of those functions come from all those 8 subcrates. So let's just look at the first one. Yeah, these are then just relatively large files. I mean, now it's only like 4,600 lines, but again, this used to be just all in one gigantic file. So yeah, that's a little bit easier to compile now in parallel, which is nice for me not having to wait around as long reasons. So again, for example, then the add acacia button function, we're taking again that mutable reference to that hash map, and we're just building out that block with the block's types, button, the different properties that it can have. It's like button face with like all the different, for the enum, all the different possible values. And then the states are just vector, and then here we are pushing into that vector all the different states. So for example, state with the ID 10,569 has the properties button face floor and button facing north and button power true. And that's actually not the default. The default is that right here, which is when it's on the wall facing north and unpowered. Yeah, I know that putting the default true false flag into every single state is a little bit dumb, but that's just how it's done in that big JSON file that Minecraft generates. Yeah, it wasn't really a problem this far. I mean, if I want to find the default value, I just have to look through all of these. Yeah, it's not quite ideal, but it hasn't been that big of a problem yet, I think. So yeah, it's been working well enough. Let's just put it that way. And now I'm already recording for 20 minutes, and I only looked at the data and data generator tools. So let's look at the library now. This is where not the majority of the code. The majority of code lives in this big data crate, of course. But the most complexity or the most interesting stuff lives in this library. Yeah, the top level, we do have some constants that I have to put somewhere. So if you spawn chunk radius and view distance, still all hard-coded values, but at some point this will go into some configuration, of course. I have a custom error enum, so I just like to do it that way. I mean, it would be probably better to have like errors depending, or have different types have their own error type or something. But yeah, that's just where I define some errors of mine. And of course also implementing display for all of those errors, and also implementing error for my error. So yeah, this just makes error handling a little bit easier, because then all my functions that can return an error can just return a box din implementing error. Yeah. Anyways, yeah, that just means that I can use the same error type everywhere, and that just makes using like the question mark operator a little bit easier. Then I don't have to like deal with different error types ever, pretty much, which is kind of nice. You have like all the different connection states in here, definitions of what the packet is and what data pack is. Yeah, these are just things that should be somewhere probably, but yeah, I haven't really found a better place for them so far. Yeah, we do have some utils, so that's also, I think, an anti-pattern to have a utils like module somewhere. This should probably also all be moved in something in like other modules or something. I don't know. But this is just 50 lines of code, and it's been working well enough for now. So you have a function here that reads a packet out of a TCP stream, which, for which we first, of course, have to find out how long the packet is. That's always fun. Because, yeah, I mean, you think about, or you hear about packets if you're dealing with like networking and things like that. But if you're dealing with TCP streams, then it's literally just a stream of bytes. You don't know where it starts or where it ends, really. So that's why packets in Minecraft always start with their length. So here we are trying to just find the length. So we have this vector of bytes. And then we allocate a buffer here that is just 0. So a vector of length of 1, or an array of a length of 1. And then we just, read from that stream and put that into our nice little buffer. No, we read into that buffer, and then we can push that value that we just read into the packet length bits. And here we just check essentially if the first bit in that byte is a 1, because the packet's length is encoded as a var int, or variable length integer. And that just means if the first thing here is a 1, then there should be another integer left. And if there is not another integer coming, then we break out of this little loop. So just look at, is that buffer, and we're ending with this, and if it's a 0, then if this is a 0, then I don't know. This works. Don't question it. I've written that 9 months ago, so it's probably fine. Does its job well enough. It's a little bit just like bitwise logic. You always have to kind of think about that a little bit too hard. At least I do. And now that we have the length of the packet, we can just construct our raw packet, which we just start out again with the packet's length. And here we just try to find out the actual length of the packet. So we are deserializing that var int, and when we know how long that is, we can set up a big vector that is the exact length then of that packet. And then we can read all of those bytes and put those bytes again into this raw packet vector. We can figure out the packet's ID, and then we can just create this whole packet struct that has the ID, the length, the data, and then also the raw data. So the packet then does not contain the length and the packet's ID, if I'm not mistaken. And the raw data is just all the data if we need this for whatever reason. I did have like a send packet function somewhere. I don't know why this isn't in here anymore. Where is that send Send packet is now in here. Yeah, right, I did change that up a little bit not too long ago. So yeah, send packet function isn't here anymore. So let's move on. Here we do also have just some UUID conversion functions, because of course in Minecraft because Minecraft uses UUIDs for a few different things, like your player's ID, for example, or for entities. And internally they're represented just as an unsigned 128-bit long integer, but for the protocol you need to have them in their like string form in hexadecimal. And depending on the use, you want them like with the dashes or without the dashes. And so here are just some functions to convert that numeric ID then to those string forms. And down here we just have like two little tests to see if this works using my UUID. Yeah, then serializing and deserializing is of course pretty important of data, right? So the deserialize module, I have functions to deserialize all kinds of data types that exist in the Minecraft protocol, like booleans, for example. So going just from mutable vector of bytes, then just taking the first one, and if it's a 0, it's false. If it's a 1, it's a true. Yeah, makes sense, I guess. I'm taking mutable vectors of bytes here everywhere. So if I pass a packet, I just put all the data in here, and then I just take all the bytes that I want to take away. And so I just can then repeatedly just call all the deserialized functions one after another. I don't have to worry about how many or how long then every single value is. For booleans, of course, it's relatively simple, right? It's just always 1 byte, but for var-ins, it's not as easy. So this just makes things a little bit easier. I don't have to keep track of like how far into that packet I've already like read bytes, if that makes any sense. Unsigned shorts, just removing the first and second byte and putting them together. Shorts in little endian, so there we can actually, here we just draining 2 bytes from the data, and then just using the from i16 LE bytes. Isn't there also like an i16 from BE bytes? Yeah. So I could probably also use that instead of doing whatever I'm doing up here. So yeah, whatever. It's working. I don't want to touch working code, right? Integers, little endian, longs, long, little endian. Not quite sure why I need little endian, like where this is used in the protocol. Right, I'm only using this then for NBT, because for NBT is quite long, and for NBT I then don't want to always remove like from the front of the vector, because that's kind of not ideal for performance. So there I'm just flipping or reversing that entire vector, and then I can just work from the back and just pop off from the back basically. And when you do that, you do it in little endian, because now the endianness is the wrong way around, or the other way around. And endianness essentially just means like if you have a number made of multiple bytes, like is the most significant byte at the front or at the back. Longs, doubles, floats, UUIDs, so that's just U238. Strings. So strings are a little bit more interesting, because for strings you also store the length. So that's just a var-int first, and then that length then for the string. Strings in Minecraft thankfully are all UTF-8, at least all the ones that I came across for now. So that's nice, because Rust also just really wants to use UTF-8 for everything, which is the correct choice, obviously. Bit sets, which are vectors of 64-bit numbers. Positions are also maybe interesting, because positions are packed into a big long, And then out of that, with a little bit of bit shifting magic, you get like the X, Y, and Z coordinates out. Hashed slots, also a thing. Hashed slots are just slots that are in like a shorter form, technically something. Different types of slot components, the things that like an item can have or something. There's different components or different things that items, or not an item, but like a slot is like a stack of items. Yeah, it's a whole thing. And then there's like the var-int code. That's also code that I probably couldn't explain now. It works. I've written some tests somewhere that all pass, and I never had any troubles with this in recent times. So but essentially it's just looking at, or just getting like the first byte out, and then just looking if there's like this continue bit set, and then just kind of advancing through that number until you have no more of those continue bits, and you're at the last byte, and you just put all the bits together somehow. And then there comes all the NBT code. So NBT is kind of interesting because there are two different forms of NBT. There's the NBT that is used for network communication, and there's NBT that is used for the on-disk storage. And both of these are just very slightly different in like how they are encapsulated. So for the different NBT tag types, it's the same. It's just that like the shell around it essentially is a little bit different. So as I said earlier, here we are directly just reversing that entire data, so we can then just always pop off from the back, which is a little bit more performant, I guess. And we just look at like what the ID of that first tag is, and then just call the functions depending on what the tag is. The same thing again for NBT that's stored on disk, and then we have all the functions for the different NBT tags. So for example, string value, the length is short in little endian, then receive the length, we can get all the bytes for that length, and we of course have to reverse those bytes again to be in like the correct order again, and we can just call string from UTF-8 on that, for example. Lists, of course, we need to look at the ID again, so that we know or can pass all the values that are in the list. Same thing then for MBT list. It's just a list of lists. I don't know what that was all about. Tag compounds are a little bit similar. Tag compounds are of course named again. Lists that the individual items don't have their name. List of tag compounds, int arrays, all of that, and then some tests to make sure this all actually works. So that's the deserialization. Serialization is just the same thing in reverse, right? Just taking a value and turning it into a vector of bytes. I don't think that I have to go too closely into this. It's just all the same, just the other way around, essentially. Again, with a couple of tests to make sure that at least var-ins work. And then top level, there's just containerclick left. So this again is a module that I didn't have any better place to put it. And this just handles like all the container interactions. If you are in a chest, you like take an item and put it somewhere else. And so for that you have the click container packet with Windows ID, slots, buttons, modes. So what button was pressed, was mode is active, and things like that. The items that are in the chest, UID of the player, reference to the global game object, all the streams that have that container opened, player inventory index, that's just because there is, because I think the starting index is 9. I think, that's just because the way that the slots in the inventory are numbered, So if you shift click, the first slot that an item should be placed in is the slot with the number 9. Stuff like that. Yeah, that's also not really very beautiful code, because it's just a lot of messy logic that's needed. And there are a lot of like different modes. So if the mode is 0, there's something. If the mode is 1, there's something. If the mode is something else, then I'm actually not dealing with that and just, I think, resetting and basically just telling the client like, hey, whatever you did, just to throw it away, forget about it. Yeah, and the actual logic, I think, is in this handle click function, but yeah, right, then we just check if there's like difference, if the new item in a slot is different than the old item or something. And when we do that, we just need to, again, send packets to the players that have that container opened. Because, of course, all the players that look into the chest should be informed about changes that happen to the slots in the chest, obviously, but players who don't look in the chest don't really care about it. And I think with mode 1 with shift clicking, I don't really remember, but all the actual handling then is in this handle click with boolean if it's left click, what the original inventory item is in that slot, what the original cursor item is, and then we return 2 slots for the new inventory item and the new cursor item. Right, so that's then when you like pick up an item by just normally clicking. So for example, if you just try to pick up an item, then your original inventory item is whatever item you just clicked, the original cursor item is nothing, and afterwards that's changed, of course. So here we then look at like if the original inventory item is like something and the slot has an item, then we need to check if the original of the cursor has an item in it. And if it has, then we need to like either swap the 2 slots, so if they're of the same item, then we of course need to like stack them up. But if we need to stack them up, we need to figure out like what the max stack size of that item is, what the count is that you have in the cursor, the count it in the chest, and then if with that max stack size we can actually just put them all down if there's enough space. Or if there's not enough space, then we need to calculate how many items are left over. So very annoying code to write, and a lot of like edge cases and little things. Similar thing for handling shift clicks, but there we of course need the entire inventory, because you can sometimes by just shift clicking on one item you manipulate like multiple stacks at once, because your one stack can spread over multiple stacks in the target inventory. We also need to figure out like because in that packet that tells us that the player clicked on something, you just have all the slots in one big array, if I'm not mistaken, and then you need to figure out like if this is in the player's inventory or in the chest, and all that good stuff. As you can tell, I wrote all of this code like 3 months ago, so can't really explain it anymore. I mean, I would need to spend some significant brain energy again to look into all of this works and to properly explain it. So I'm just gonna quickly go over it. The good thing about this component is, or this module, is that it's relatively well tested, I think. So as you can see, there are a lot of tests in here, like shift click to chest with items, stack up lots, right? So original chest inventory, we have 20 items, the item ID 1 and the item count 63. The player inventory is pretty much empty except for one stack with also the item ID 1 with 12 items. And then we click the right slot, and then we handle shift click, and then we assert that now 12 items are now item count 64 instead of 63. And there's like one left over or multiple, I don't know. Just kind of making sure that everything works. So there's like 1,800 lines, but yeah, 1,500 of this is just a test. So yeah, and then we have types. Types are also important. So we have the big world type, which is responsible for storing the entire world. Yeah, world is just a hash map of dimensions. We have a world loader, we have a default spawn location. Dimension then is just a hash map of chunk coordinates and chunks. And entities. And the chunk is a chunk coordinates with a vector of the chunk sections, how long it's been inhabited, when the last update was, if the light is on, if it's been modified since I've last loaded the chunk. So that's important so that I don't have to save chunks again that haven't been modified, of course. And then a list of the block entities in the chunk. Chunk section is then just a vector of blocks, or the blocks IDs, a vector for the block, for the biomes, skylights, block lights. Yeah, world. We have a function to create a new world. So there we take in the world loader and we look if the loader is initialized. So if it is, then we can load an existing world. If it's not, we have to create a new world. Save to disk, we just go through all the dimensions and call save to disk for all of them. A new dimension, just go through the spawn, chunk radius and insert new chunks. New from loader, there we load from the disk loader, load chunk here. Get chunk position, yeah. Get chunk from position and mutably. So just taking a block position, getting out a mutable chunk, and yeah, also immutably or from a chunk position. Function to override a block, that's of course very important. That's for like setting blocks, of course. So there we need to again get the chunk. We need to figure out if that block is actually in a valid height range. And then we can call a set block, or we can also get a block. I think this is something that I've also optimized just a few days ago here. So for that, I now am actually storing the chunks in a hash map. Before that, it was just in a big vector. And then I had always to like search through the entire vector. And now with the hash map, it's just a much quicker lookup. Yeah, calling get block on the chunk. Save to disk. Yeah, there we just call loader save to disk with that, with the chunks and the dimension and all of that good stuff. Getting all the entities in a chunk, adding an entity or add multiple entities. Here generating a new chunk. So my chunk generation at the moment is just like making the lowest section of the chunk stone and the rest air, which is relatively simple, of course. When we set a block, we of course say that the chunk is now modified. You get that position within that chunk. The ID of the chunk section, so sections is of course a 16 height always, and then the block ID. So that's the current block ID. It's just the block IDs are in a big vector, just how it's stored in the protocol or on disk. So from the chunk position, we now have to like take the X and the Z times 16 and the Y times plus 64 and section ID times 16 and it all times 256 for reasons that probably make sense. And then we can look into the section, and if this section is actually empty, because I don't store data for all the chunk sections that are just air, because that's just wasted space essentially. But if we want to set a block in such a chunk section, then we need to first fill it with data, of course. And yeah, then we just can put in at the right location that new block's ID. And yeah, we also may need to destroy a block entity when you override a block that has a block entity attached. So there we just check if there is a block entity at that location, and if there is, then we say the block override outcome is destroy block entity, which we then have to do something with in another place. And if we do have a block entity, where does if the block entity So in the block entity module, if we call new from block on that with the block state ID, then we may get a new block entity out. So that's when you place a block down that has a block entity assigned to it, like a chest. And if you do have that, then we need to also put that block entity into the chunk. Then we just return that block override outcome. Right now, this is just used for if the block entity needs to be destroyed, so that's why the variable name here is not ideal. It should be just block override outcome probably. Then just getting the block state ID from chunk position. Again, needing to do some math here to figure out like where in this 4960 long vector the block is at that position. Trying to get like block entities or a mutable version of the block entity. And then for transmission over the network, we also need the count of non-air blocks. That's just like a performance optimization of Minecraft, and here we just look at all the blocks and filter all of those air blocks out, and then we count what's left. A world loader is then just a trait actually, because the idea was that I can implement different world loaders for different, things. I don't know. The idea was to maybe be able to like store a world in like a database or something. But for now, I just have the vanilla world loader that is just made to load vanilla worlds. It takes like a base path and then we implement world loader. So that's the load chunk function at this block location, at the chunk location. Again, here we now take in this big block state hash map. We get the path of the region file. We check if it exists. If it does not, we just generate a new chunk. We open the region file. We look at the chunk's position in the header of that file. So the file starts with a header with two tables, one for where then all the chunks are stored in a file, and also the time when they were last modified, but I don't really care about that here. And that's just 4 bytes per chunk, so we just have to then we just can calculate based on the chunk's coordinate where we need to go essentially. And then we can read only what we need to read, which we're doing right here, and seeking and getting like all the actual bytes that we need out of that, because then the chunks are stored in, I think it's 4 kilobyte long blocks of data, but there may be some padding at the end, so there's like an actual length then. So we first need that table to figure out like where does the chunk start in the file, and then at the front of that there's some metadata like the actual length in bytes that we need to like figure out. There's also a compression scheme because the chunks data is compressed typically. So I need to figure out whatever the compression scheme is. Right now, Minecraft seems to only use the compression scheme 2, which is zlib. So I only have that implemented for now. Then once we have the uncompressed data, we can just deserialize it with the nbt disk deserialization function, which works pretty well because of course the chunks data is just nbt data. And then we also have to look at the status of the chunk, because Minecraft also stores like half chunks, or chunks that are like in some generation phase. I don't want those here, so I'm filtering those out. And then just looking at the different biomes ID for the, I get the biome IDs that you basically just cache them, so I don't have to call this get biomes ID function every time I need it. And then we just go through all the chunk sections and, for those, just like pull out of the data, all of that, like the biomes, the blocks with their properties and their block palettes. I made a video about like all the chunk loadings. I think I will just like skip over that for now. Loading entities. Entities are stored in their own kind of region files that are made up exactly like the chunks. So I pretty much just copied that. And I'm looking at the entity type and then just deserializing that. Is initialized, just then looks if the level.dat file exists. Saving, again, everything in reverse. function to write a level.dat file, a basic one at least, that contains the spawn and simple stuff like that. Saving entities to disk. So for saving, I'm always just saving the entire region instead of just a single chunk, because that was always a little bit easier, because sometimes you need to like shuffle around the different like chunks, because now when one chunk suddenly gets bigger, then all the chunks that come after it now must be shuffled back. So I figured this is just the easier to do it that way. Saving entire region into chunk to disk. Just essentially everything in reverse again, pretty much. And then some tests, some basic tests. And then we have block entities. So that's something that I've just recently like pretty much rewritten. So this is very different from the video in which I implemented block entities originally. So this is just a big enum now, not a struct anymore. An enum that has a variant for every type of block entity. And those then contain a specific struct for just that block entity that then carries the data that is relevant to that block entity. There's also a trait that I then implemented for all of those. Just ticking, generating a new one, getting their contained items mutably or owned. Then ticking, just calling the tick functions, new from block, calling the new from block functions, getting the position out, getting the ID, getting their contained items, removing themselves. So if you delete a block entity, setting if they need to tick, if they checking if they need to get ticked. For now I only implemented furnace ticking, so I only have that in there for now. And then just some conversion to NBT or from NBT. And then also just a enum with just the different block entity IDs, which for now was useful, I guess, still. And converting then a block entity ID from just a string. And then all these actual block entity things live up here. So there's just one file per block entity. For very simple ones who don't have data, like bell, it's just the position and the vector of components, which is like, I think, the slot components of then the item originally. I don't know if I need that, but I have it in here. It's really unused at the moment. And just the tick function is just returning itself. New is just taking the position and just constructing the struct. Essentially, they don't have any items. So, for example, chests are a little bit more interesting, maybe. Here's a chest. This has now an inventory. So, of course, we need to initialize that inventory. We need to have the contained items getter function. There's a little bit more work then to be done for the NVT conversion. Furnaces might be interesting because they have, of course, their ticking, which I already implemented a little bit. So there's just essentially looking at, can I smelt something or not? For now, I only implemented smelting using coal and raw iron. So very simple. And just sending packets out to everyone, I guess, which isn't open just the players who open that inventory. So only players who actually look at the furnace then get updated about that state, like how much lit time is remaining or what is the current progress, that sort of stuff. We have commands. The different command parsers, that's just for like all the properties that a command can have, their numbers and their nodes. Like all the commands are just essentially one big tree graph like thing with like all the different arguments that are possible or not possible. Or that was also interesting to figure out. And commands also have an execution function we will look at a little bit later. They take just the command as it was typed, I think, and then an optional TCP stream and then a reference to the game object. Connections are extremely simple. entities are not. So entities I use a trait for right now. I want to rewrite them the same way like the block entities, but yeah, that will come soon. There's just some enums for like entity tick outcomes, AI behaviors, AI execution results, and then yeah, creating a new entity from NVT and all that good stuff. Yeah, just some functions to work then with like entities. If they collide with a block somewhere, if they're on the ground, or if they are on ground in a different position. Getting the hitbox of the entity, getting their occupied block positions. That's again for collision checking at a different position. Yeah, this is just really ugly code at the moment. Executing AI behaviors like moving towards player or wander around or idling. And executing those functions. Like wander, we just do a bit of a random like X or Z offset. Yeah, I will need to look into this a lot more in the future. And also converting an entity to a spawn entity packet, just because that seemed useful. Savable entities, then also to NBT and NBT extras and all that good stuff from NBT. So because I have just a trait, it's impossible for me to ever get like at the actual data of an entity, which is a little bit of a problem. So for example, I now have common mobs, but then the function up here somewhere to get common entity data or get common mob, if I call that on not a mob, then that's bad. So that's why I really want to have that enum set up as with the block entities. And right, this down here is just then testing code where I set up like a testing mob. All the actual entities live in here that I've implemented so far. Like for example, a creeper. A creeper has like common entity data to it, like position, velocity, UIDs, that sort of stuff. The common mob data because it's a mob. And explosion radius, a fuse timer is ignited or is powered, but those things I have no chance of getting at. That's why creepers currently explode instantly. So yeah, because I can't get at the fuse or at the fuse timer or whatever. So here a new, we have some extra NBT that we can then use to populate all the structs fields, and also saving in reverse, of course, and yeah, returning things like the proper hitbox, getting the mob data, that sort of stuff. Yeah. That's entities. Then we have the global game object. That's just containing a vector of the players. Those are in a mutex, so that this needs to be locked because the game object is shared across different threads. And then for multi-threading, you, of course, can't access the same thing simultaneously from multiple threads. So you need to lock them behind a mutex, for example. The entity ID manager, that is there to create new entity IDs, so that I don't accidentally have doubled entity IDs. The commands, the last save all timestamp, so when the world was saved the last time, when I sent the keep alive to the players the last time, then we have the block state data. This does not need to be in a mutex because we never write to it anymore, we just read from it, which is fine. The connections and the packet send queues, those are a dash map, which is a parallel hash map implementation. So typically you would need to lock the entire hash map if you want to work with it. But with the dash map crate, you can use different values in parallel from different threads, which is kind of nice. And then the packet handler actions that we then write to, this just because I don't want to handle all the packets immediately. I want to do that in the actual tick loop. And then we have like save all to just save the entire game, everything. And then now here is the send packet function, which is relatively simple now because this just uses those packet sending queues, and then we just look at the value of that peer address. And that's now pretty important that it's using a dash map because every player, every connection has its own thread. And if this was just a big mutex, then I would need to like log, and if I want to add a new packet to the queue, I would need to log the entire queue for all the connections. And now I just essentially just logged the map for that one connection. And those are the different kinds of packet handler actions. So the packet handler then will return one of those. NBT is just some stuff to work with all the NBT. So we have an enum of the different tags. A tag is always a string and then a value, and then the list tag is just the value without the string. We have a default implementation. We have then all the different functions to get all the values out. Pretty much, getting a description or then converting a tag to a specific type. So now let's take a look at the player module. So a player has a position, again, yaw, pitch, velocity, display names, UIDs, and a lot of that kind of stuff. Players are a little bit interesting because the player is kind of an entity, but also like special in a way, of course. Function to just clone a player. I need to implement this myself because TCP stream does not implement clone, just try clone. So we try cloning it and then unwrapping, which might not be the greatest thing ever in the world, but it works for now. Implementing then entity for player because that makes certain things a little bit easier. And then we implement stuff for the player struct, like a new function, so we can create a new player easily. And I think here we are also immediately then saving the new player. Or no, we check if the player actually has some data saved already. If it does not, then we create a blank new player. If the player has some data, then we just get the player data from disk. Again, players are stored as NVT data. We have a function to save a player to disk. We have a function to get the item that the player currently has in their hand, either in the main hand or in the offhand. And that's just, a specific position in their inventory. The offhand has its own inventory ID, but the main hand, of course, depending on which hotbar slot you have selected. Getting the cardinal direction the player looks in. So this is just, if it's looking like north, east, south, or west. And that depends on, in what range the yaw is, essentially. Setting a new position for the player. Interesting here is, of course, that if the player's position changes, then we probably also need to send new chunks to the player. So we also check that. I recently also fixed that because it used to be that if you teleport, this code would just fall apart because I always just assumed that you just move like one chunk over at a time, which of course, if you just run around normally is always the case, but not if you teleport around. New position and rotation. This is just some relatively basic stuff like that. Getting the pitch, sending a chunk then to the player because then we need to construct this gigantic packet. Here recently I also now implement support for the different block state paletted containers. So I'm not quite sure if this all is like working properly, but for now this seemed to be fine. And then we actually do this, call this game send packet function, which then just again puts it into this nice little queue. And then we'll get to that later, but the queue can then just be sent asynchronously or from another thread. Just utility function to get the path where the player data is, or the file for that player. Getting or setting which slot is selected. If you of course change the selected slot, then we also need to set the new set equipment packet to all the connected players, because then the player has another item in their hand maybe, and then people need to be informed about that. Getting the inventory, setting slots. setting the entire inventory, things like that, opening some inventories, then we need to send them like an open screen package, and then also the container content. So you then use that contained items owned function of a block entity, for example, closing inventories, setting if the player is sneaking, or getting if it's sneaking, and getting their position as an entity position. That's all the player stuff. Block positions are relatively simple. Or actually, we do have now block and entity positions. There used to be only like a block position type that was just called position, but now I've split those two up. Block position is of course X, Y, and Z. Y only is a 16-bit number because the world is not as high as it is wide. Converting to the position in chunk, so that's just kind of clamping everything down to just get chunk positions, which is necessary then again for getting the specific block out of a chunk, for example, or convert to like chunk coordinates, entity positions, converting between block and entity positions, calculating distance between two entity positions, subtracting, adding, multiplying, dividing entity positions. Just some utility stuff to make my life a little bit easier. And just some more tests. Slots, I'm not quite sure what's in here, just some definitions for what a slot is, what an item is. Item get the entity. So this is, I think, if we want to summon like an item on the ground. Default implementation, again, NBT conversion stuff, converting from an item to a slot, because those are like slightly different things for reasons. Different slot components. So I think we also looked at those in the deserialization, serialization stuff. So this could also probably moved into here then, but and then just some ID things. I think that's like mostly it here. We do have blocks, so those are just some implementations for different types of blocks. Get block state ID, right? That is when you place a new block, then depending on like a bunch of different factors, like the faces, the kernel directions, the pitch, everything pretty much depends on what the block's ID actually is. It should get placed, right? For stairs, for example, this is the curve stair. If it's upside down, that sort of stuff. And here for every type, I then have a module for that. Or also updating if like an adjacent block changes. So for example, if you have two stairs next to each other, you destroy one, maybe the other one changes state, especially for like fences, essentially. And block interactions, handling those. So for example, do we overwrite something? Do we open an inventory? Do we need to open a sign editor? Do we do nothing? For example, for a door, if we interact with the door, then we need to do a whole bunch of stuff and essentially just check if we now need to open or close that door. Getting the ID or the state, we need to look into what direction the player was facing when placing the door. We need to check do we place or which side is the hinge on. Bunch of stuff like that. What is the block ID next to the door? If it's a valid door, we need to check if it's like a double door, then the hinge needs to go on maybe the other side or not. This again, like a ton of code that just has like so many special cases that you need to think about. And then I wrote tests for all of those, because that just makes actually life a whole lot easier, because then you can just run your tests and know like, okay, does everything still work correctly? Because for these, I like to kind of just build up the functionality a little bit over time, but then for more complicated things like stairs, for example, it gets out of hand really fast. So this is just all that code here is just for checking like in which shapes and which cardinal directions and all that good stuff. And yeah, so I have a lot of tests here. There's like 4,000 lines of tests pretty much. Those are blocks. Block entities looked at packets are something that are maybe still interesting. So this is the main module. So we have a trait for packets. Getting the packet's ID, the target, and the state. Packet ID is actually constant because that then means that we can match on that. And getting the protocol version and the version string, which I didn't find a better place to put apparently. And then packets are just like kind of sorted neatly into whether they're client bound or server bound. And then the different connection states. So for example, for play, you have a whole bunch of packets. Like a set entity metadata packet that contains the entity ID and then the metadata, and then packet ID is that, and it's targeted client, connection state is play, and then we have, for this we also define entity metadata in here. That's maybe a bit of a bad example, but set container slot is maybe easier. Just from container slot so we do the serialization here, output a vector of bytes, and we just append, and we're using all these serialization functions, and the other way around with all the deserialization functions. So I think I don't have to look at like all the packets, because then we would still sit here tomorrow. I think that's it with the library actually. So then there's just proxy and server. So we can maybe look at the proxy first. The proxy is just one big file, actually not even that big, just 400 lines. And here we're just starting up a TCP listener, and then we just listen for incoming streams. Of every stream we do some connection tracking, spawn a new thread to handle the packets coming in on the server side, and then another one for the client side. And it's just like packet parsing, and then just passing those packets then onto those packet functions out of the library. I'm not looking at all of them, but for some that are interesting, I do like the whole deserialization and then serialization again, or the other way around, depending on which direction the packet travels. So that's why I also implemented the deserialization and serialization for every single packet. So typically you would only need one of the two, of course. But having the proxy means that I can test all my packet implementations then against the official vanilla Minecraft server, which just makes testing some things a little bit easier sometimes. I also want to write my own Minecraft client in the future, for mainly just for testing. So it's not going to be like a graphical client. It's just something that I can use to programmatically test my server better. And then I also, of course, need to have access to the serialization functions of all the packets, or the deserialization functions. But that's just the proxy, relatively simple. This is then the actual send packet function. Used to be in the library, but now, because I'm using like those queues, it's not in the library anymore. It's now implemented in the server. So I had to copy this into the proxy as well. And I wanted to not have it in the library anymore, so I don't accidentally use it. So server is again relatively simple, I would say. So just initialize the server here, set up, the TCP listener. We get all the block states here again once. We set up the world loader with the path to the world. Initialize the entity ID manager, and then we just put this onto this big game object. We initialize the commands. We then can put together this game arc so that we can share this across threads. Initialize terminal inputs. We clone then this game arc, and then we move this into the new thread for the main loop. And then we just set up new threads for we just listen for new listeners coming in. We make a new game connections entry. We set up for the receiving side a thread where we then just loop through and just constantly listen for new packets coming in. If we have a new packet, we use this read packet function. And then we call the handle packet on that, and we do something with the packet handler result. So we disconnect the player if we get an error, or we put this into this game packet handler actions queue. And then we sleep for like a millisecond. I think this is good for performance or something. I don't know. I've been trying with this a little bit, because of course it would be much better to have this be like asynchronous and using like Tokyo or something for that. But I don't really want to do that. I wanted to like not do anything asynchronously and just do multi-threading the hard way, just for learning purposes mostly, right? If this was like a proper Minecraft server, you should really just use Tokyo. But I want to learn things, so I'm doing things the hard way sometimes. I think because effectively it's just an endless loop, I think I've been like burning a ton of CPU cycles needlessly, so I've tried to combat this a little bit by just sleeping for like a millisecond. Introduces, of course, a little bit extra delay, but it's just a millisecond, so who cares? And then on the transmit side, that is now relatively new. So we go through then the send queue for that player and then send out the packets that are in there. Because before then, I had in the packet handlers like, okay, for like a movement packet, for example, receive a movement packet from a player, so now we need to send out the movement packets and to all the different players to inform them about the player movement, and that's like happening synchronously, and nothing else can happen for this one player during the time. Yes, now it's just all a little bit trying to just put this like network IO into separate threads basically. Here we're then sending a packet, so we are serializing the ID. We put down the packet, we do the length somewhere, data length, plus the serialized ID and length of that, and then we append all this together, and then we just write it and send it out over the network. Flush the stream, always very important. Function to disconnect the player. So then we just do some like cleanup and inform the still connected players about it, and remove the player from wherever it needs to be removed from. And then there's the main loop that's just always constantly running in circles. We calculate the start and the end time. In between that, we do the actual tick, and then we can check the duration, and then we can sleep for the appropriate amount of time, because a tick should always happen every 50 milliseconds. So if we just take 10 milliseconds, for example, then we need to sleep for 40, so we stay in like the correct rhythm. Or if we took longer than 50 milliseconds, then we print this out to the console together with all the tick timings and how long it took, and then I can maybe check what happens. And then the tick is just here we're just timing all the different steps, and then the different steps are like doing all these packet handler actions, like disconnecting a player, moving a player. So that we get the player, we get the old and new position, and we check if the position or the rotation is updated, and depending on that, we send out the appropriate packets with the correct values. For this, for example, we calculate deltas, so we don't send out absolute values. But again, I'm not gonna go through all of this code. You can look at it yourself if you really want to, because it's just a ton of plumbing things together, basically. Here we send keeper lives, which we do in a separate thread, which in the separate thread we then do send. I'm not sure if this separate thread is still needed. But yeah, we look at if the player is still connected by looking, like, can we get some data out of that stream? Is the stream still there? And then we just send out a keep alive packet. Taking block entities, just calling all the tick functions, all the block entities, tick entities, pretty much the same. But here we also have some outcomes, like should the entity remove itself if it was deleted, or like a creeper exploded. And if that tick was, if that entity was updated, then we just save that. Or we say that a chunk is now modified here. The actual packet handlers are now relatively simple. You just get in the packet, we look at the state that the connection is in, and then depending on that we look at the packet's ID, and then we call the appropriate function from down here. Yeah, these are all the functions, and these are typically relatively simple. For like the login and the configuration states, I'm actually doing a little bit of work in here. But for the play state, it's just setting up this packet handler action thing and just putting this into the queue so it can be processed later on. Commands are maybe interesting. So those are all the commands that I currently have implemented. I think I also showed this in the video at some point, and nothing much has really changed since then. Yeah, so all the commands initialize themselves, and by doing so they push their data into this global game object again. And when a player joins, they need to be informed about all the commands that exist. So here we just create this packet for that. Just going and setting this packet up and going through all the commands and all their stuff and things. And processing their arguments, which is doing something probably. Yeah, then like a simple, like something like a ping command, we initialize the command on startup. So there we then push into this game commands vector, the command with the name ping, the execute function, all the arguments that exist. And the execute function is just a standardized function that just takes the command, the stream, the game, and then in this case, if the command was ping, we say pong, or otherwise we just return whatever the player wrote somewhere. I don't know. And right, we look at the stream. The stream is just an option because you can send commands from the console, and in this case there is no stream. So in this case we just print it out to the console, or if there's a packet, we call this game send packet again with the system chat message. Yeah, and I could look through all the commands, but then this would again take a lot of time. I'm recording now for 1.5 hours already, so yeah. Terminal input, we're setting up a separate thread there, so yeah, that's just because here we need to essentially just wait for a new input, and that would block the entire thread, so we can't do this in like the main thread somewhere. We need to do this in its own little thread. So we're just reading lines, this just blocks until there's a new line to read in. And yeah, just look at if there's like slash in front, then it's a command. If it's not, then it's a message that gets sent out to all the players. If it's a command, we just do like the whole command execution thing. And that's it. I think that's all the code. So yeah, I've now recorded again for 1.5 hours, so I expected this to go maybe a little bit quicker. Yeah, so I will have a lot of fun editing this. I hope you enjoyed this little video. If you have any questions, please let me know. And then I can maybe go into some more detail for certain parts. I will also make sure to link the current commit that we looked at today in the video description, so that you can also look at the code yourself in the state that it's in right now. Yeah, so I guess that's already it. Thanks for watching. If you made it this far, congratulations. And yeah, well, thanks for watching. See ya pretty soon, hopefully, with a new big update. And yeah, because we are gonna start in survival mode pretty soon. That's gonna be fun, and we'll also change a lot of code again, probably. So thanks for watching. See ya then. Have a great time. Bye bye.